In this series of videos, we're going to look at Lagrangian mechanics. Specifically, we want to understand what a Lagrangian is, what action is, and why is the action minimized? Why is the action stationary? This is something that always puzzled me when studying, and it's something that I only recently figured out. Before we go ahead, we have to warn you. While we want to understand Lagrangian mechanics, the only way that we can successfully do it is by using Hamiltonian mechanics, because Lagrangian mechanics is essentially a subset of Hamiltonian mechanics. So if you haven't seen Hamiltonian mechanics, you should wait to watch this video. So first thing, let's review the math together. Lagrangian mechanics starts with Hamilton's principle of stationary action. We have a function called action that for each possible trajectory gives us a number. And the actual trajectory are the ones such that the action is minimized or is stationary, so that a small change in the trajectory does not change the action. The action can be written as the integral of a Lagrangian, and Lagrangian is a function of position, velocity, and time. Now, the problem is that unfortunately, this way of writing does not help us to understand what is going on geometrically. What is going on geometrically is not apparent if we just look at this space and at this trajectory. So we need to rearrange things a little bit. As I said before, we are going to be using elements of Hamiltonian mechanics. Specifically, what we need to do is to use this relationship, that the Hamiltonian is equal the momentum times the velocity minus the Lagrangian. So we take this relationship, we substitute it here, and we have this result. Now, one of the things we don't like here is that here we have a function times a derivative. Here we have another function, but we have no derivative. So to make things a little bit more symmetric, let's add a derivative. We add dt, which is 1. So multiplying the Hamiltonian by 1 does not change anything. So now we have function times derivative and functions times derivative. Now we note that the Hamiltonian is a function of qpt, and this is also a function of qpt, it's just of p, but we do not have a derivative in p. So let's add that. So now we have three functions, p, 0, and minus h, and three derivatives, dq dt, dp dt, and dt dt. This is the form, this is the way of writing the Lagrangian that we are going to need. Okay, so how can we arrange a little bit these terms and how to understand this equation a little bit better? Well, first of all, we know that we are working on QPT space. So we are considering the space of QP, phase space, extended by time. So this is the space of all states at all times. And then we're going to have a trajectory here that corresponds to all the state as time moves on. So note that t has a double role here. T has a role of a coordinate, so we could make a change just in the direction of t, which corresponds to the partial derivative, but also t is the parameter of our trajectory. So a total derivative in t would correspond to moving along this line. So we should not be confused by this double role. Now we can take the derivatives in time and put them together and form a vector field. We call this vector field S, and this is a displacement for the states in time. So if we have a state here, this state is going to evolve in time in a particular direction, and this S is going to tell us where do these states move. So a trajectory is going to be a line that it's always tangent to S, that is going to tell us where those states are moving. Now we can collect these three scalar functions, again, make a vector field. So we're going to have that theta is of components p, 0, and minus h. Now we don't know at this point what this vector field is. It's going to be important later. But what we do know is that the Lagrangian is simply the scalar product between theta and s. You can see that you take the first element and the first element of here, you multiply them, and so on, and you sum them. So now that we know what the Lagrangian is in this framework, we have to go and look at the action. What is the action? Well, the action is the integral of the Lagrangian, and Lagrangian is the scalar product between theta and s. So we're taking theta and making the scalar product on S, and then we are integrating. But S is the tangent of our trajectory. So what we're actually doing is simply the line integral of theta along the trajectory. So what the action is, in terms of these new symbols, the action is simply the line integral of theta along the trajectory. So to recap, we have a vector field theta. We have a vector field S, which is the displacement. It tells us where the states are moving. The Lagrangian is a scalar product among those two. And the action is the line integral of theta along our trajectories. And the Hamilton's principle of stationary action tells us that the line integral of theta along the trajectory is stationary. If we make a small change here, the line integral of theta is not going to change. Now, if we now want to understand Lagrangian mechanics, we need to understand exactly what these pieces are. We already know what S is. We don't know what theta is, so we need to understand what this is. And we need to understand why its line integral is stationary, it's minimized along the actual trajectories.